Welcome to this section on performance measurement and validation and testing. In this section, we shall see how the performance of a sequence-to-sequence model is measured. More specifically, a sequence-to-sequence model used in neural machine translation. Previously, we had been introduced to very popular metrics which are used for evaluating the performance of a machine learning model, like accuracy, precision, recall, the number of false positive rate, true positive rate, true negative rate, false negative rate. Now we shall be introducing the BLEU score, or the BLEU score, which stands for bilingual evaluation under study. Now the score is very commonly used in tasks like machine translation, where we are very much interested in making sure that when we have, for example, this kind of expected output, our model output should look as much similar as possible to the expected output that we have right here. Another model, or another possible model output we could have in this case is M. Another one is M apprentissage approfondi. Let's now go straight into seeing how the BLEU score is calculated. So suppose we have this output G, or GM, which is 1, 2, 3, 4, 5. This is J 1, 2, 3, 4, 5, 2. So the expected output is this, and then the model output 2 is this. Now for each of the model output value or words, as for this first word, because in this case this J is considered as a word in our vocabulary. So if, for example, in this first output right here, the 1 hot representation corresponds to G, as we've seen here, we are going to look in the expected output for the number of times we have G, or rather we're going to look for in the expected output to see if we actually have G. So we're gonna look for the number of times G occurs in the output, in the expected output. So right here we have G occurs once, so we have 1, plus we go to the next M occurs once, and then we go to the next M. But note that while moving to this next M, we've taken off the fact that this M, or this M belongs to this M. So this M, once we get to this M, there is no more M left right here. So at this point we have just G, M. But by the time we move to this other M, this is what our expected output is. So instead of having the GM, we've taken them off because these two have already taken this 2 off. So anytime we have a correspondence, we take the G off. For example, like in this case, the G is gone and here the M has gone. Now when we get to this point, we're left with no M, so we don't count that. We go to this, left with no M, this left with no M, so we don't actually count that. And now we have just 2 which corresponded, and that's why we have 2 divided by the total number of model output. So here we have 1, 2, 3, 4, 5. So in the output right here we have 5, so we have 2 on 5, and our BLEU score is equals 2 on 5. Now note that if we didn't take this off, the G and the M, when we had already counted them, we would have had a BLEU score of 5 on 5, telling us that the model's output is very perfect. But that is erroneous because this model output doesn't look exactly like the expected output. So that's why it's important that each time we have the matching, we take the word off from the expected output. We're going to be comparing later on with the other words. Now let's move to the next. For this we have G, it matches, we take G off. M, it matches, we take M off. L, it will still match, so we'll be left with this. Take L off, we're left with apprentissage approfondi. Apprentissage matches, approfondi matches, and at the end of the day we have 5 matches divided by 5 model outputs, giving us a BLEU score of 1, which is the perfect BLEU score. Now we move to the third possibility. In this case we have M, which matches, apprentissage, which matches, and approfondir, which matches. This is not actually 4 on 4, it's supposed to be 3 on 3. So we've modified that, that's 3 on 3, which is still 1. But now, note that these two outputs, or this model output 1 and model output 3, give the same BLEU score, but don't have the similar translation, or not, they don't have comparable translations, as the model output 1 has clearly a better translation than the model output 3. So what we could do is to penalize model outputs which are shorter than the longer model outputs, and to do this we use the brevity penalty. We use the brevity penalty. Now how does this work? Suppose we have R and C, where R is the number of words of the translated model. So in this case we have 1, 2, 3, so R is 3, and then C is the number of words the expected model output, or the expected output. So here we have 1, 2, 3, 4, 5. So when R is greater than C, in this case that's not the case, we have a brevity penalty of 1. So we don't actually penalize the model. And when R is less than or equal C, the brevity penalty equals E, that's exponential to the power of 1 minus C on R. And this will be multiplied by the BLEU score to give a new BLEU score, which actually penalizes models which produce shorter outputs. Now let's look at some examples. Right here we have a brevity penalty, E to the power of 1 minus 5 on 5. R is equals 5, as we could see, 1, 2, 3, 4, 5. C is equals 5, as we could see. But now if we apply this second formula here, right here, it gives us 1 minus 5 on 5, which is e to the power of 0, which is 1. So 1 times 1 will still give us 1. Now let's look at the next. For the next, we have a brevity penalty of 1 still. So 1 times 2 on 5 will be 2 on 5. And lastly, we have this brevity penalty of e to the power of 1 minus 5 on 3, because the number of words we have right here equals 3. So that gives us 0.513. And now the final BLEU score we have from here is not 1, but 0.513. So that's what we get for this model output 3. And this permits us, or this now tells us that the BLEU score for model output 1 is greater than that of the BLEU score for model output 3. Let's now build the BLEU score metric in TensorFlow 2. Before doing that, we could add it to the compiler as a metric. So we have the metrics equals, we'll call it the BLEU score, so we'll just call it the BLEU. So we're going to create a metrics class here, which actually inherits from the TensorFlow.keras.metrics.metric class. It has a function update state, which will permit us to do computations with respect to the BLEU score, and then output the results with the result method. As you could see in the result method, we have the self.add and then the self.total variables, where the self.add will permit us calculate the number of times a word or words in the predicted output will match in the expected output, while the self.total will calculate the total number of words found in the predicted output. So in this example, this will permit us, or the self.add will give us a value of 2 at the end after adding up all the matching words, and then the self.total will give us a value of 5. And as we have seen, to obtain the 2, we go for each of the words, we match it up. This word we match, next word is no more, the next word no more, next word no more. So only adding this 2 gives us 2, and then all the number of words equals 5. That said, once we have this and we've seen how to compute that, all we need to do now is to calculate to find the final value for this and then the final value for this after going through each and every word in a particular output sentence. Now the output sentences come as y true and then y pred. Y true is the expected output sentence, and y pred is the expected or is a model outputted sentence. But then they come in the form of a one hot representation, like the y true is one hot and this too is one hot. So in order to easily work with these outputs, we shall instead come up with the output before this one hot representation. And that's why right here we have the argmax of the y true, and then at the negative we select the -1 index. Let's take a simple example. Suppose we have this a equals 3 1 0. Let's say a equals 2 1 0, and then we take this one hot representation. Say b is equals tf the one hot of a, and depth equals say 3. We print out b. We see that we have the one hot representation right here. Now in order to obtain a back from b, so let's suppose c, we need to get argmax of b, and then we'll select the -1 index since we're taking from this last index actually. So we run this, or let's print out c at once. So we run this and we'll see that we obtain a actually when we do this. That's when we get argmax of that. So it means in our case where we have the one hot representation, this will permit us get the output sentences as these numbers, which will be like some sort of words. So when we have a number like 2 or 1 or 0 outputted, now we have the actual word which was outputted. So we shall not compare the words as we saw on the slides. We shall compare instead their corresponding positions in the vocabulary. So that's why after this we'll leave from. So before we had an output of batch size. So before we had an output of batch size, let's write it right here. Batch size, the sequence length, and then the vocabulary size. And after this we now have instead the batch size, the sequence length, no more vocabulary size. So that's it. Now we're going to see how to work with the y pred and the y true at once. To do that, we go through using the zip function. Now, so for all I, j in zip of this, so I will work with the y pred and j with the y true. If you're not very versed with the zip, we could take a look at that. Suppose we have this a, and let's define a. Let's just copy this, and then we'll define a. Let's say a1, and then we have a2. Now that's what we have right here. Let's now change this. Let's say this is 5, 6, and then let's maintain that at 0. So if we want to print out, if we want to say for I, j in zip of a1, a2, and then we'll print this out, print out ij. You see how it's going to print out each and every value of a1 and a2 while respecting their indices, so, or their positions. So right here we have 2 and 5, we have 1 and 6, we have 0 and 0. So that's just what the zip function does. Now that that's understood, we should understand that in this for loop right here, the zip function is used to select each and every expected and then model output sentence or outputs in every batch. Now recall that here we have this batch size, so we have this for every batch, or let's just say we have for example a batch size of, let's say 32. So we have a batch size of 32, and then we have this, or let's take even the batch size we had chosen earlier. So we have the batch size of 512 and then 10. Now here what it's going to do is it's going to select each and every batch. So we just have 1, so this is what's going to enter, and then not actually this, but something like this, because we've selected just one of that. So the shape is not going to be like this. So the shape we're gonna have of the wirePrep is gonna be something like this. But what is interesting to notice that is actually for each and every batch that we're gonna do that comparison. So that will permit us actually work faster. Now we have this total. What's the use of the total? We have seen already in the slides. It's basically counting the number of words we have in the output sentence. And to do that, we have the model output here. I represents the model output. That's wirePrep that we can see right here. So to compute this total number of words in this outputted sentence, which in this case is a tensor, we'll simply find the number of non-zero values in that. So if, for example, we have, because suppose we have is now something like this, so we have 2 2, and the rest is zeros, say zeros. So suppose we have something like this. Now what happens right here is we are not going to say that these parts, for example, are part of the sentence. So we just have to count only this and this. So this function permits us do that, and that's why we have that. And now we do this self total plus equals this, because for each and every batch we have to do, or supposing that we are working with 512 batches totally. So if we're working with 512 batches totally, we want to do this computation for all the 512 batches. So that's why we just have that. Now we've selected a particular batch, or we've selected a particular output that's of wirePrep, which is now represented as I. So for every word in I, so for every word in the output or in the model outputted sentence, we call this the model, and then this is the expected. So for every word in it, the word here is represented by this P. Let's just say word. So for every word, let's say for every word we'll say P, we just change it to word. Right here, let's say word. Let's make it clearer. That's fine. Okay, so for every word in I, if the word is equal 0, like we see here, we just stop. We just leave this batch because we're done already. Now, that's it. We break. We leave this loop, and then we move to the next one. We leave this word actually. We move to the next sentence. So if we get into this, like for example here, if we get into this, if we get here, fine. We get here, fine. If we have a 0, we'll leave this and we'll get to the next batch, which is from this next loop. So we've left this loop already. Now if this is not the case, like if we get to this point, if we're here, right here, we'll now compare this and this value with all the values in the, let's say, let's do this. Let's have, for example, 3 1 2, then 0 0, right up to the end right here. So suppose we have this as our y true, and then this is our wirePrep. So we're supposing that we have this as our wirePrep, and then this is our y true. Now what happens here is we go for each and every word in I, as we've seen. So for this, we write here. Now for every cure, so we'll say again here for word, let's say for word, let's just maintain cure. So we have for every word, that this cure is for every word now in this range, or we're not going for every word of cure in J. Actually, we're going for every word or for every cure in the range of the length of cure. If the word, like if this word that we had from here, so if this word 2 matches with J of cure, it's just like saying if this matches with this, we do self.add and we break out of this. Breaking out of this simply means we should not go through all the other words in cure again. We should just leave that, and then we'll move on to the next word right here. So because this is the loop we are in, and now we also get into this loop so that we could compare this particular word we have chosen with all the different words in this. So if this 2 matches with 3, for example, it doesn't match, so we continue. We go to 1, it doesn't match, we continue. We go to 2, it matches. So what happens? We add with them, that is, we add the self.add variable. Recall that in this we had already computed the total for that particular I or for that particular model output. So we know the total number of words in our sentence. But here we're interested to know if each and every word matches. So 2, for example, for now matches. But recall that if 2 matches, like if we have this 2 that matches with this 2, we have to make sure that when we get to this 2, there is no more 2 right here, so that we don't have to compare this 2 with this 2 that has been matched with the previous 2. So in that sense, we have to take off this, and to take off this, we use the Boolean mask. Let's see how the Boolean mask works. So suppose we have this, we could start something like here. So suppose we have this, and then we have, say, A equals, let's just use A equals 1 2 3, and then we have B equals TF, the Boolean mask of A, but this time around we have true, false, true. Come down here, we print out B. We see how this A has been printed, but only when the Boolean max had true. So we have 1 and 3. Now if we change this, let's change this into a true. We see we have it back. Now if everything is false, obviously you have something empty. So we have this, run this, that's great. So basically that's what we do, and that's what the Boolean mask does. So what we're gonna do right here is, as you could see, we have this J. So we have this guy right here. This represents our J, because as we see, we have selected the batch, the Y true. So we have the Y true, which is this, and now it's passed into the Boolean mask. Now we define this TF, that constant, but we could take it off. We're just taking a list, and that works fine. So we have this. Let's take this one off. Okay, so that's fine. Now, so we have a false if the I equals cure. Now in this case, this I isn't the same I we had here, so let's just modify this. So let's call this a Y. So for Y in this range. Okay, so we have a false if Y equals cure, else true. But we're doing this for Y in range J. Now recall that this is, so our range J in this case is basically all these values. So for all these values we have right here, we are always false if the Y is equals cure. Now why do we do this comparison? Recall that for now we have selected a particular cure. So supposing we have selected this cure to be 2. So suppose we are at this point, because we've gone through, we've selected this 2, we want to compare it, or we selected this other, suppose we selected this 2 and we're comparing with this, the word is 2, and then cure is this. So we've selected this. Cure isn't actually 2, cure is actually the position 2, and it happens that the value at the position 2 is 2. So cure could be 0 1 2 3 up to the length, as we had seen here. It's not like here where we just selected the values. Here we went in the range. So for cure in this range, as we had seen, so we are at this point exactly. Now if here we have cure, which is 2, and we're saying that if we get in right here and we have that 2 which matches, because we cannot get actually inside here if it doesn't match. So as we saw here, we have if the word matches. So if there is that match, it means that this particular cure needs to be taken off. So if that cure matches with the Y, because Y basically is, here we're basically using this Y to go through all the J. So if the cure matches with a particular Y, we'll send it to false. So this will obviously turn this into true, true, false, because it's going to match right here, since we had cure equals 2, and also our word equals J cure, and so Y is going to get into here, and then Y is going to match at that value. So we're going to have this 2, since Y is going to be equals cure. Now the rest is going to be false, so that's it. The rest is going to be true, rather, that's it, and then only this is going to be false. So in that sense, when we leave from here, the J now has all the values except 2, and that's how we take that off. And obviously we break off from this so that we don't continue going and testing other values which are not going to be useful. Now if it had fallen in this, so if we're at this point, we'll see that first of all this wouldn't match with any of the previous values. So since it doesn't match with any of the previous values, we wouldn't even get to this point. So we'll just continue testing with all the other values. Now we could also add another here. We could also say if the value of cure, so we could say if, because if we're testing and then we get to a point where we have 0, we should normally stop because that's a pattern. So if cure equals 0, or rather if j of cure, so if j of cure is equal 0, we should also break out from this. So that's fine. And then okay, so that's it. So from here we see how we actually do this, add up, and then we also add up the total, and that's fine. So let's run this, run that, run this. Let's reduce this to while training we could train faster like this. So let's do that, run this again, and right here we could add the validation. So we could say validation data equals validation data set. So we've added that, and then we run this. Now we have tried to train and we've gotten this error, zip argument must support iteration. So let's see how to solve that. To solve that, we could work in eager mode. So we could say run eagerly equals true. So that's fine. Run that in eager mode. We have another error. Yeah, x and y must have the same z type. After we run it again, we have another error where we're told that j has shape 10 before loop, but this after one iteration, which is normally what we are doing actually when we get into this. When we get to this level, with j's value or j's shape is going to change. So we're told to use this to set shape invariance. Now we insert this right here. We're going to put this right here. Normally that should be fine. We'll run that again. I will say that we'll start training. Now the brevity penalty hasn't been included in the calculation for the BLEU score. So as an in-class exercise, you can include the brevity penalty. After training for several epochs, we obtained the following results. As you can see right here, we're living from a loss of about 5. Now we're going down, and then the BLEU score too is produced. As you can see, we have a BLEU score for now of 0.14, and it takes about 23 seconds per epoch. So to speed this up and to demonstrate faster how the BLEU score is going to increase, let's just take this off from here. We should take off this metrics, take this off. We run now in graph mode and no more eager mode, because the eager mode is going to be slower. And then for now, let's just do without the validation. So let's do this, take this off, and then run this again. So we forgot to take that off. Okay, so from this we could now run this. Now after training for about 1,000 epochs and having a quite small loss, let's now add this, and then you shall see how the BLEU score is gonna increase. So from this we could let's just run this, and we could have the validation data equals validation data set. So we have that. We'll run this now, and there we go. We have a loss of 0.2, BLEU score of 0.71, validation loss 0.6, BLEU score for validation 0.70. So with this, we've actually seen how to train and evaluate a machine translation model. Now let's go ahead to see how to do testing.